Are you aware of the numeric form of the stress tensor? When you're working through your tutorial sheets, you might bump into it, like this one. Often, no unit is given. Today, we are going to find out how the stress tensor can appear in this number form and whether there's any implied unit behind these numbers or any other working convention for that matter. Watch until the end and you will gain a substantial boost in the conceptual understanding of the stress tensor. At the end of this video, I will tell you why the numeric form of stress tensor is worth discussing and also share with you my study tips. This is a soft example that I adapted from a textbook. The solution is straightforward. By right, we can move forward to the next question happily after plugging in all the numbers and getting the answer. But there is more we can learn from this question. What catches attention immediately is the numeric form of the stress tensor. Here comes our first query about this question. Here is a possible visualization of this problem. How can the stress tensor appear in numeric form like this? Do these numbers even have a unit? First, we address the unit issue. Do these numbers have a unit? Absolutely yes, these numbers have a unit. Stress is force by surface area, so sigma would have the unit of pressure. The SI unit of stress is Newton per meter squared, although some other units are also possible. The unit needs to be stated explicitly in formal communication. There is no such thing as implied unit where no unit is stated explicitly. But in less formal situations, when things are clouded by complex or intensive mathematics, the unit is sometimes withheld for highly focused communication. Where is the unit normally withheld? Well, in research settings, I can tell you, the unit is normally withheld in the lab experiment logbook. Go back to example 1a. No unit has been given for the numeric stress tensor, probably because the intention of the question is to test the learners on applying the formula. We take note that the question wants to keep the unit open, and we go with it by not indicating any unit in our answers. However, if the unit has been given, for example, kilopascal, we should indicate it in our answers. Unit issue settled. Now, we'll see how the stress tensor could have appeared in this numeric form. First and foremost, we need to know that the stress tensor is a function of position and time, meaning each component of the stress tensor matrix is a function of position and time. The functions can be this, or this, depending on the flow system. At a particular time instant, the stress tensor at point P is numeric. Because the stress tensor sigma is generally symbolic, we can denote the numeric stress tensor as sigma Pt1. What about at steady state? The time terms vanish and the functions are reduced to this. Once the flow reaches the steady state, the stress tensor of the flow system is a function of position only. Noting that sigma is a function of x, y, z, and t, we conclude that the stress tensor appears in numeric form for a specific location and time instant. This example says that at point P of the liquid flow system, the stress tensor is this. This means either at a particular time instant, the stress tensor takes these values, or at steady state, the stress tensor takes these values. A rising question now is the stress tensor constant at steady state? Before a steady state, sigma is a function of position and time. At steady state, it is just a function of position. Is the stress tensor constant at steady state? Our answer is both yes and no. Yes, it is constant with respect to time. No, it is not constant with respect to position. The key concept here is the stress tensor sigma is a function of position and time. If you find this video helpful, can you please let me know by hitting the like and share buttons or leaving me a comment in the comment section below. Consider subscribe also if you want more of such animated educational videos from my channel. You might be wondering why I discuss the numeric form of stress tensor, a topic that looks so trivial that it cannot be a topic at all. Actually, this has something to do with the motto I've been sticking to throughout my learning journey. That is, small problem, big knowledge, it's not small at all. Under this learning spirit, I look at simple problems from various angles and perspectives and try to learn as much as possible from the simple problems. Why simple problems? Because they are rid of unnecessary complications that might get in the way of optimal learning. Looking at simple problems is actually my number one study tip for acquiring solid understanding and intuition, which is essential for solving complex and open-ended problems. Subscribe to my channel and I believe you are on your way there. Let me give you an example. For the stress tensor, I brought to you the symbolic and the diagrammatic form in previous videos. And in this video, the numeric form. Studying the various forms of the stress tensor enables us to look at the stress tensor from various angles and multiple perspectives. And this goes a long way towards gaining a solid and substantial overall understanding in stress tensor or any other subject in general. Once again, don't forget to hit the like and share buttons. I'm Kyle Tan. See you in my next video.